We're going to discuss, in this lecture, discuss common polar graphs, specifically lines, circles, cardioids, limicons without inner loops, limicons with inner loop, rose curves, and spirals. Now, the goal, for the most part, is not to do these with a calculator, to make these graphs with a calculator, not to make these graphs by plotting points, but by recognizing features, recognizing forms, so that we can sketch a graph rather rapidly, knowing enough information. So that's what our goal is. We're going to start first discussing what the equations of lines look like. And we've already seen a little bit of that, but that's what we're going to start with. So the first type of line, and we're looking at the simplest types of lines. The first type of line would be something where we had theta is equal to an angle. As an example, theta equal 3 pi over 4. Okay. That would be an example of a type. And let me remind you then what this is going to really look like. We're going to take the tangent of both sides and replace then tangent. We'll go through an example, but we've seen this already. In this case, the line would be y is equal to the tangent of whatever the angle is, beta, times x. So the slope of the line is tangent of beta, and of course the line goes through the origin. The line passes through the origin. It has a slope of tangent of beta. Well, and that's not completely accurate, I guess. It does have a slope of tangent of beta. That is true. Second type that we will look at, and we'll do some quick examples here, is if we have something that is of the form r times cosine of theta is equal to some constant. We'll say constant a. Well, in this case, that is a simple vertical line, because r cosine of theta can be replaced with x. And so this ends up being x equal a, which obviously is a vertical line. And the third, of course, would be something like r times sine of theta is equal to a constant. Let's say like b. Well, we can replace r sine of theta with a y, and so this would end up being y is equal to b, which of course is a horizontal line. So, real quickly, let's graph three different lines of these natures. Okay, for instance, if we had theta is equal to 3 pi over 4, remember that what we would do is our first step would be, let's take the tangent of both sides. That is, the tangent of theta is equal to the tangent of 3 pi over 4. 3 pi over 4. And the tangent of theta can be replaced with y over x. That's one of the identities that we have. And what's the tangent of 3 pi over 4? Well, let's see. Here's 1 pi over 4. Here's 2 pi over 4. Here's 3 pi over 4. The tangent there is negative 1, isn't it? And so we would have, multiplying both sides by x, we'd have y is equal to negative x. And so we could now easily graph that. And if we did, of course, y equal negative x would actually be a line that looks like this. Now, if we had a situation where we had r times cosine of theta is equal to 4. Well, the r cosine of theta, as we've seen before, can be replaced with x. So this is nothing more than x equal 4. And, of course, we know that that's a vertical line through the value x equal 4. the point I'm making here is it would be quite a mess to deal with trying to plot points, or even, even solving this for R and putting it into a calculator. We'll say this is where 4 is for X. And so what we're talking about is this vertical line. So, I mean, we could do this in a little more formal way where we're just thinking in terms of polar coordinates, but these examples, of course, make it much easier. R times sine of theta equal 3 as an example. Well, r sine of theta can be replaced with a y, so this is nothing more than y is equal to 3. And so, of course, that's a horizontal line that goes through the y value of 3. So we'll suppose this is where 3 is. So we have a horizontal line. Now, a couple of other things to be said. Let me say over here parenthetically, we might see something that looks like r is equal to 3 times secant of theta. Secant, I'm sorry here, of theta. And we might struggle with how to graph that, but if we stop and think about what secant of theta is just what, 1 over cosine of theta, so this is r is equal to 3 over cosine of theta. And then we could easily multiply both sides by cosine of theta. Well, now we want to turn our attention to circles. And as we do this, again, we're not really just interested in any type of circle that we could get, that is the formula for any particular circle, but it is nice to recognize some that we'll see over and over. And so let me let you know what the forms are going to be, and then we'll discuss each one of them. So one form we'll see where we have simply r is equal to a constant. And that's really just more or less telling us the radius of the circle is a particular number. We saw earlier how r, we would square both sides, and so r squared equal a squared would be what we have, and r squared is x squared plus y squared, and so we ended up getting a circle of radius a, assuming a is positive, that is, a radius a that's centered at the origin. So we have a circle that looked like this, and of course right here, this radius, this distance, is the is the a value. Second, there's a couple that look very similar next. One is if we have r is equal to 2a times cosine of theta. Okay, 2a times cosine of theta. And we're going to discuss this more fully here in a moment, but this will be the equation of a circle, and the radius of this circle is going to be the absolute value of a, indicating in this case we might have a positive or negative a. That is, if a is a negative 4, this would read r is equal to negative 8 cosine theta. And the center of this circle, is simply going to be a comma 0. And so, a comma 0, pardon me. And so if a is a positive number, it will be on the right side of the y-axis. If a is a negative number, it will be on the left side. But in a kind of a general terms here, if we were to graph this on a rectangular coordinate system, and we're assuming right now a is positive, just so that this can show up, here would be the center. Okay, if that's where a is, this would be the center. And since this has a radius that's the absolute value of a, then from the center to the origin is a measurement of a units, distance of a units. And so we would have a circle that actually touched here, okay? So we would have a circle that looked like this. Of course, to play like that's a circle. That's pretty ugly, isn't it? Now, we could also involve a sine theta rather than a cosine theta. So another possibility would be r is equal to 2 times, we'll say, b sine of theta. Now, again, here we will have a circle. and the circle will have a radius that's the absolute value of whatever that number b is. And the center of this circle will be 0, comma b, which means it's actually on the y-axis rather than the x-axis. So if we were to do a real quick sketch of this circle, then remember the center is at 0, comma b, so we'll say this is where b is. This would be when b is positive. When b is negative, we would be going in the opposite direction. But that's the value of y where we have b, and once again, that's the center, but the radius is the absolute value of b, and that's the distance between b and the origin. And so the circle goes this distance again. It touches here, so we'd have a circle that looked like this. And once again, this radius is the absolute value of b. Up here, the radius happens to be the absolute value of a. Okay. Now, there's one more type of circle that I want to mention, and that's when we have a combination of these. Suppose we had something that looked like this. R is equal to 2a cosine of theta plus 2b times is the sine of theta. Well, in this case, the radius, okay, in this case, the radius is going to be the square root of a squared plus b squared. And the center is actually going to be a comma b. So in this case, here's what we would have. Suppose this is where A is, and suppose this is where B is. So the center is right here. But the radius is the square root of a squared plus b squared, which happens to be the distance from the origin to that point. And so in this case, the circle is going to be a little bit bigger, but it's actually going to have this radius, so it's going to touch there, isn't it? And so it's going to be something that looks like this, except that's supposed to be the center that I've got written there, a comma b. So we'd have a circle that looks something like that. Well, before we actually graph any of these, I would like to take maybe example 2 generally. We did something like this earlier when we were converting equations, but I'd like to take the form so that we can see what's happening here of R is equal to 2a times cosine of theta. Looking at that form. Well, what I'm going to do is I'm going to multiply both sides by R, so I end up with R squared is equal to 2ar cosine of theta. Now the r cosine of theta can be replaced with an x, can it? And the r squared can be replaced with x squared plus y squared. So this becomes x squared is equal to 2a times x. I'm going to gather my terms to one side. So I'm going to subtract 2ax on both sides, and I'm going to put the x's next to each other, and then, of course, the plus y squared equals 0. Now I'm going to complete the square on these two terms involving x. So the way that's accomplished is we take the coefficient of the term, of the x term, the first degree term, and we divide that by 2. Well, if we do that, of course, we get a negative a value, don't we? And then we take that negative a value and we square it. And when we do that, of course, we get a squared. Okay, so to complete the square, we need to have a plus a squared on the left side, going along with that x squared and minus 2ax. And we already have a plus y squared. And so we need to also add a squared to the right side since we added it to the left. So we'll add it to the right side there, and we have a squared then. Now on the left side, x squared minus 2ax plus a squared actually factors as x minus a, the quantity squared. And then we have plus y squared is equal to a squared. Well, now we can see that this is the equation of a circle. Remember, the equation of a circle in general looks like this. Okay, that's what the equation of a circle in general looks like. And in this case, the h is the a value. Let's come up here now. Okay, the h is the a value, and so the center of this circle, well, the center is the x value is a, and the y value is 0 because we're subtracting 0 from that y, aren't we? So there's the center. Now the radius, well, whatever we square to get a squared is the radius. And so we just have to be a little bit careful here. The radius, in this case, if a is a negative number, for example, if a is a negative number, then negative 4 squared, we couldn't say the radius is negative 4. We'd have to say the radius is positive 4. And so the radius we get out of this is actually the absolute value of a, ensuring that we have a number for the radius as a positive number. Now this matches exactly what I mentioned up there in example 2 of the style. And this is the reason that we can make that decision. Okay, so what I would like to do next then is to make a few graphs, well, I'd like to graph 3 circles, and I'll do that on the next page. Okay, the 3 equations that I want to graph are r equals r equals 7, r equals 4 cosine theta, and r equal negative 7 sine theta. And in the first example, I hope that comes to be clear to us when we're graphing r equals 7, that really that's just telling us that we're 7 units from the pole to have it. It doesn't matter on the value of theta, is what I'm getting at. It doesn't matter the value of theta, no matter what angle we consider. Even if it's angle 0, then when we're on angle 0, we've got to be 7 units from the pole. So if this is where 7 is, then we would have to have that point on the graph. Likewise, if we had an angle of pi over 2, well, it doesn't say anything about the angle. We're always 7 units from the pole. So if this is where 7 is on the y-axis, we would be there. And all of the angles, we would have to be 7 units from the pole, which just is telling us that distance here has to be 7, because that's what r is. So that's simply the radius in this case, isn't it? Although r doesn't stand for radius generally, that's the idea behind this. So the first one we have done pretty simply. Now in the second example, graphing r is equal to 4 times cosine of theta, remember what we're trying to make this look like. We're trying to use the model r is equal to 2a cosine theta. That's the model we're trying to use. And if we use that model, we know then what the center and the radius is going to be. The radius will be the absolute value of a, and the center will be a comma 0. So as we look at that scenario and we consider our model, we notice that the 2a is what's the coefficient of cosine theta in the model, and the 4 is the coefficient of cosine theta in our actual problem. So simply a must be equal to 2. Well, once we know that, then what we've got for sure is a circle whose radius is absolute value of 2. Oops. The radius then is simply 2. And the center is 2, 0. Well, then that's pretty easy for us to graph. We'll make a quick sketch here. Okay, so the center is 2 comma 0, so we'd move out here 1, 2 units. There's 2 units. There's the center, and the radius is 2. So if we move in all directions, 2 units will be on the circle, including if we move from the center to the left 2 units, we would be on the circle, so that point's on the circle. And of course, directly up 2 units is on the circle, and directly down 2 units is on the circle, and directly right 2 units is on the circle. So our circle will look like this. Whoops, sorry about that. This would be where 3 is, and this would be where 4 is. So there's our circle. Okay, in the next example, r is equal to negative 7 sine theta. Now again, we're trying to match a model. We're trying to match a model, and that model would be r is equal to 2b sine of theta. And if we can get that model, then we know that the radius is the absolute value of b. And we also know the center is going to be 0 comma b. So we're after finding b. Well, in a similar fashion that we did a moment ago, what we end up with here is that the 2b is the coefficient of sine theta in the model, and the negative 7 is the coefficient of sine theta in the actual equation. So 2b and negative 7 must be identical. And as we solve for b here, we get b is negative 7 over 2. Now we're going to leave it as negative 7 over 2, but of course that's useful to know that that's negative 3.5, isn't it? So here we have a circle whose radius is the absolute value of b. And so in this case, the radius is 7/2, 3.5. And the center then is 0 comma b, 0 comma b, and b is negative 7/2. Well, now we're set up. Okay, let's see if we can't draw this circle. I'm going to be a little more careful. Okay. There's the y-axis. I guess across here I'll do the x-axis. Now the center is at, and let's assume here's 1, here's 2, here's 3, here's 4, here's 5. The center is 0, negative 7.5. Negative 7/2. And so that's 0, negative 3.5, isn't it? So 1, 2, 3.5 is right here. Okay? So there's negative 7/2. Now the radius is 7/2. So that distance right here is the radius, isn't it? And then we need to go down further, though, don't we, to get this graph in here. We know that this point's on the graph. Okay, and if I go down further, let's see. What do I have? 1, 2, 3, 4, 5, 6, 7. I believe this point will be on the graph because that's 3.5 from the center. And if I go left and right, let's see. I believe 1, 2, 3. I believe about right here would be 3.5, and I believe about right here would be 3.5 units the other direction. And of course, that's a pretty big. Remember, this radius is 7/2. So my circle would look something like this, and you don't know that you have agreed that you won't laugh at my circles. Of course, I can't hear you laugh right now, can I? But there's the circle that we get in this case. Now, a couple of notes that I would like to make before we move on to the next type of graph. If we were plotting points, in the case of r equal a, to create the whole graph, we would have to use every theta value. It takes theta values that are between 0 and 2 pi. I mean, we have to have all of the angles between 0 and 2 pi, because for each angle we've got to plot a point. And so it takes a full rotation, that is, to get all of those points in there. But on the other hand, if we're looking at something that looks like r is equal to 2a times cosine of theta, to plot all of these points, to get all of these points, to make this full graph, it only takes thetas between 0 and pi. Now we actually, let's see if we actually have to use pi. I don't think we actually have to use pi. So we get a full rotation by not needing every single point. Now, let's just take an example up there where we had r is equal to 4 cosine of theta. Now notice, let's just make a little tiny table here. Okay. Notice when we choose theta, of course, to be 0, then when we calculate, and I'm looking at the one above, okay, this where we're actually using r is equal to 4 cosine of theta. When theta is 0, cosine of 0 is 1, and so r would be 4. And so that's this point way, see, I'm drawing up here, way out here to the right, isn't it? And if we choose theta to be equal to pi over 2, okay, if we use theta to be equal to pi over 2, notice that then the cosine of theta is equal to 0, isn't it? And so r would be 4 times 0, which would be 0. And the point 0 comma pi over 2 means we look at the angle pi over 2, and of course that's the vertical line that corresponds to the y-axis there, doesn't it? But since r is 0, then we don't move along that at all. And so when theta is pi over 2, we're actually at that point that I just filled in. And then, of course, I've skipped a lot of values possible for theta. If we choose theta to be equal to pi, then what we have is the cosine of pi is negative 1. And so r is 4 times negative 1, or negative. Before we look at additional graphs,